Hi, welcome to Intermediate Algebra. We are doing an overview of exponential and logarithmic functions. And I'm Bethany Sansing-Helton, and hopefully you're one of my students. So we're going to start out talking about these concepts by having you watch a short video on YouTube, and you can see the YouTube link right here. So if you go on and write it down and then type that into a browser window and watch that video so you get a sense of what an exponential growth looks like and some idea of what it is before we continue. That'd be great. Okay, assuming you've already seen the video about exponential growth, this is an example of an exponential growth curve. So an exponential function, an equation that you would create to draw that curve, is in the form f of x is equal to b to the x, or y equals b raised to the x power. So what makes this different than a polynomial is that now the x is in the exponent. You've done things before with a quadratic, where it's x squared, where the x is the base, the b part is actually x. So these are totally new. They're exponential functions. They're called transcendental functions because you can't just use your standard rules of algebra to solve them. So they're a little trickier and require their own special explanation. So if you graph it, you need to be comfortable with your laws of exponents. If I graph g of x equals 2 to the x, then I'm saying, well, if x is negative 2, I would substitute the x into the exponent, so 2 raised to the negative 2. Knowing your laws of exponents, that's the same as 1 over 2 squared. So I know 1 over 2 squared is 1/4. Similarly, 2 to the negative 1 is 1 over 2 to the first power, so that's 1/2. 2 to the 0 is 1, because anything raised to the 0 power is 1. 2 to the first power is 2, and 2 to the second power is 4. And so when we graph it, it looks like that graph off to the right. The domain is all real numbers, and the range, as you can see, has this limit, this horizontal asymptote as the x-axis. Now, the base can be anything we want it to be. If instead the base was a fraction, and I raised a fraction to an x power, if you think about that, if I raise 1/2 to the negative 2, then to make it a positive exponent, I would flip the fraction over, so that would be 2 squared. So when x is negative 2, y is 4. When x is negative 1, y is 2. So you can see this different set of values, and this is what is called an exponential decay curve. Exponential decay. So those are both examples of exponential functions. The base can be anything we want it to be as long as it is not 0 or negative and not equal to 1. Now, the reason it can't be 0 is because 0 raised to any power is still 0. The reason it can't be 1 is because 1 raised to any power is just 1. So both of those conditions would just give us a horizontal line. The reason it can't be negative is because if you raise a negative number to an even power, you get a positive number. But if you raise a negative number to an odd power, you get a negative number. So you don't get a curve that looks like this exponential growth or exponential decay. So it can't be negative, can't be 0, can't be 1. But those are our only limitations for the base. Now, it's very important, again, that you recall your laws of exponents. And I have a worksheet that you can fill out with all the rules of the exponents that are on here. And you can access that worksheet in our Google Drive folder as well. So if you haven't printed that out, you might want to pause and print it out and then fill in all of the information for these different exponents that you see here. Because if you don't know your laws of exponents, you're going to have an extremely difficult time working with exponential functions. All right, so let's solve some exponential equations together. So can you figure out what x is if 2 to the x equals 8? Pause if you need to really think about it. You should get that x equals 3. And why do we know that x equals 3? Well, because I know 2 cubed is 8. So we can figure that out. But you could also think of it as another way. I know that 8 can be written as 2 cubed. So I could write 2 to the x is equal to 2 to the third, right? Because 8 is the same as 2 cubed. So now I look at this equation, and the left-hand side has a base of 2, and the right-hand side is a base of 2. And hopefully it makes perfect sense to you that if the bases are the same, the exponents must be the same. And that's actually a special rule for dealing with exponential functions. If you're lucky, then they follow this rule. If you have the left-hand side and the right-hand side with the same base, then you can send the exponents equal to each other. So in this case, our example above says that since I have a base of 3 on the left-hand, of 2, sorry, on the left-hand side and right-hand side, then that means the exponents must be equal. So x equals 3. Here's a more complicated example. 3 to the 2x minus 1 equals 81. Well, I know that 81 is 3 times itself some number of times. And maybe I don't remember how many, and so I might just count off on my fingers or use a calculator. 3 times 3 is 9, times 3 is 27, times 3 is 81. So that's 4 3's. So 3 to the 2x minus 1 is the same as 3 to the 4th power. Now I have the left-hand side and the right-hand side having the same base. So again, I can set the exponents equal to each other. So 2x minus 1 equals 4. And then I just have to solve this equation. So I add 1 to both sides, and I divide both sides by 2, and I get x is equal to the fraction 5 halves. It's okay if x is a fraction. If we go back in here and substitute 5 halves for x, 2 times 5 halves is 5. 5 minus 1 is 4. So I get 3 to the 4th, which is 81. Now, so these are very lucky cases, basically, where I can get the left-hand side and the right-hand side having the same base. What if I had some equation that was like 2 to the x is equal to 5? Then what's x? How do I have any idea what x is? And in order to solve equations like this, we need to understand the next kind of function, which is logarithmic functions. So I'm going to end this first screencast, and the next one we'll talk about logarithmic functions, and I'll demonstrate how to solve exponential and logarithmic equations using those special functions. So part 1 done.